With today's diverse technology, the need for viewing electrical phenomena is greater than ever. The device most commonly used to view electrical events is the oscilloscope. Oscilloscopes display electrical events by drawing a graph that shows amplitude on the vertical or y-axis and time on the horizontal or x-axis. So the scope lets us see the amplitude of an electrical event over a calibrated period of time. In this program, we'll use a block diagram of a typical oscilloscope to show you how an oscilloscope displays both vertical and horizontal information. We'll illustrate the operation of major functional blocks and how they relate to front panel controls. And we'll use a Tektronix 2235 as our demonstration oscilloscope. The best way to visualize how an oscilloscope works is to split the display into two parts: the vertical portion and the horizontal portion. This diagram shows the functional blocks commonly found in oscilloscopes like the 2235. The vertical section is composed of the vertical input coupling network, vertical input attenuator, vertical input amplifier, the delay line, and vertical output amplifier. The horizontal section includes the trigger circuit, horizontal sweep generator, and horizontal output amplifier. And finally, there's the cathode ray tube, the CRT. Any signal we connect to the oscilloscope follows a path through the vertical and horizontal circuitry on its way to the CRT display. As we mentioned earlier, the oscilloscope can be divided into two sections, the vertical and horizontal sections. In this part of the tape, we'll take a closer look at the signal path through the vertical section. Source signals are connected to oscilloscopes through probes or through coaxial cables. After a signal source is connected to the vertical input BNC, the signal flows through the vertical input coupling network. The coupling network allows selection of either DC, AC, or ground coupling. DC provides a direct path to the vertical amplifier, coupling both AC and DC components of the applied signal. AC coupling blocks the DC component of the applied signal by inserting a capacitor in series with the input. Ground position disconnects the signal and shorts only the attenuator input to ground. It does not short the applied signal to ground. After an applied signal flows through the coupling network, it passes into the attenuator block. The attenuator provides a constant high-impedance load to the probed circuit, typically 1 megohm or 10 megohms with a ×10 probe. A constant load assures that any circuits after this point will not affect the source of the applied signal. The attenuator block also provides a means for reducing the signal to a desired level, creating a usable display on the CRT. In short, the attenuator block does two things. It provides a constant load for the applied signal, and it allows signal reduction of the applied signal. The first amplifier section encountered by the applied signal is the vertical input amplifier. In this block, the signal is attenuated or amplified for convenient viewing. The front panel controls related to this block are volts per division and vertical position. The calibrated volts per division control lets us select the desired signal size. The vertical position control moves the signal up and down for convenient positioning of the signal when making amplitude measurements. The best placement is on a CRT graticule line. For example, after positioning a signal on a graticule line, we can count the major vertical divisions and determine the signal amplitude. The signal is 5 major divisions high, and the volts per division control is set at 2 volts per major division. So the signal is 5 divisions times 2 volts per division, which equals 10 volts peak-to-peak amplitude. Following the vertical input amplifier, the next block the incoming signal encounters is the delay line. This line delays the signal output from the vertical input amplifier for a short period of time. That way the horizontal sweep generator circuitry has time to initiate a sweep before the vertical signal reaches the CRT vertical deflection plates. This coordination of vertical and horizontal timing by the delay line lets us view the signal's leading edge. Without delay, the signal would look like this. With delay, like this. The next block, the vertical output amplifier, provides additional amplification of the signal. Compared to the levels of some input signals, it takes a much larger voltage to deflect the signal vertically on the CRT. In fact, it typically takes anywhere from 2 to 10 volts to deflect the beam one major division. So if the incoming signal is only 10 millivolts, it'll need a large amount of amplification to deflect the beam to a viewable size. For the 10 millivolt signal and a CRT with a 10 volt response, that would meet an amplification factor of 1000 to show a CRT display of one division. From the vertical output amplifier, the signal is applied directly to the CRT's vertical deflection plates. We've examined the signal path through the vertical section. Now let's follow the signal path through the horizontal section. The input signal is coupled from the vertical input BNC to the trigger circuit. The trigger circuit takes a sample of the incoming signal and shapes it. This shaped trigger signal starts the sweep, thus ensuring horizontal stability of the trace by beginning each sweep at the same point in relationship to the incoming signal. Without triggering, the trace would free run. Each sweep would start at a different time, resulting in a confused collection of unmeasurable traces. So a triggered sweep scope starts each sweep at the same time by triggering at the same point on successive repetitions of the input signal. In the 2235, there are several trigger modes: peak-to-peak auto, norm, TV field, TV lines, and single sweep. Peak-to-peak auto trigger mode means that the trigger level control range is set by the input signal peaks, and the sweep can be triggered by input signal rep rates above 20 Hz. If no trigger signal is present, the sweep free runs, providing a reference trace. Normal trigger mode causes the sweep to run only when a trigger signal is present. If no trigger signal is present, or if the level control is misadjusted, the CRT does not show a trace. TV field triggering permits triggering on the vertical interval or field of television signals. TV line triggering synchronizes the oscilloscope sweep with television horizontal sync or line pulses. Single sweep triggering mode, as the name implies, allows only one sweep to occur when the trigger is recognized. The horizontal section contains the sweep generator, also called the time-based generator, and the horizontal output amplifier. Here are some signals generated in the horizontal section. The sawtooth waveform has several parts. The rising portion is called the ramp. The falling edge is the retrace. The time between ramps is called the hold-off time. Here are the blanking and unblanking pulses which are applied to the trace intensity circuit. Now let's look at each of these signals in more detail. The ramp controls the rate at which the trace is drawn horizontally across the face of the CRT. The primary function of the sweep generator is to produce linear beam movement in the CRT. In other words, the sweep generator makes sure the beam moves at the same rate from start to finish. If the sweep generator doesn't move the beam at the same rate, accurate time measurements are impossible. A calibrated control called seconds per division lets the operator select many different sweep speeds. The faster the beam is drawn across the CRT, the faster the time reference. If this control is set at 0.5 seconds per division, the time reference over the full 10 major divisions is 5 seconds. If it's set at 5 milliseconds per division, the full time reference is 50 milliseconds. This accurate time reference is controlled by the rate of the rise of the sawtooth waveform produced in the sweep generator circuit. Another function of the sweep generator is CRT blanking and unblanking. The word blanking means turning off the electron beam so nothing is displayed on the screen. Unblanking means turning the trace back on. Typically, a blanking pulse is a negative square wave, while an unblanking pulse is a positive square wave. Without some means to turn the beam off, we'd see retrace with every sweep. Here's what retrace looks like on a real scope. With blanking, when the trace reaches the right side of the screen, the beam is turned off while the sweep resets to the left. When the sweep starts again, an unblanking pulse turns the trace back on. The sawtooth signal that's produced by the sweep generator is fed to the next block in the system, the horizontal output amplifier. It amplifies the sawtooth signal to a level sufficient to deflect the beam horizontally across the entire face of the CRT. Now let's examine the last functional block in our simplified look at an oscilloscope. The cathode ray tube is the output or display section of the oscilloscope. CRTs come in many shapes and sizes. Storage tubes, miniscopes, and display monitors require very different configurations, but all operate on the same principles. A typical CRT consists of a heater, cathode, grid cup, the focusing ring, the accelerating anodes, the vertical and horizontal deflection plates, the mesh, and the post-deflection anode. The electron beam is generated by the heater and cathode. The heater heats the oxide-coated cathode, which then emits electrons. As the electrons are attracted toward the first anode, they pass through the grid cup. The grid limits the number of electrons passing through the hole in the grid cup. Electron flow is controlled with the front panel intensity control. Now the focusing and accelerating anodes start shaping the electron flow into a narrow beam. Spot size is adjustable by using the focus control on the front panel. Next, the beam is deflected by the vertical and horizontal deflection plates. The post-deflection anode accelerates the electron beam. Between the post-deflection anode and the cathode, there's a high potential difference, around 10 to 24 kilovolts. This difference in potential accelerates the beam to the phosphor on the screen. The mesh reduces compression and improves trace linearity. Finally, we have a bright, clear trace on the CRT that's a controllable representation of the signal being fed to the oscilloscope circuitry. With a better idea of how a CRT operates, let's see how the CRT circuitry uses signals from the vertical and horizontal sections to produce a display. The electron beam that makes the display on the face of the CRT is negatively charged. Without voltage applied to the deflection plates, the beam will strike the center of the CRT. We can deflect the beam because it's attracted by positive voltage and repelled by negative voltage. For this discussion, let's assume we have a CRT with a vertical deflection sensitivity of 10 volts per division. So to move the signal up one division, instead of attracting it with a 10 volts positive signal, we can apply a 5 volts negative signal to one deflection plate, which essentially pushes the beam away, and apply 5 positive volts to the other deflection plate to pull the beam. This concept is called push-pull. The process is used primarily to improve the linearity of the display and allows accurate measurements over the entire viewing area. Push-pull signals are equal in amplitude and opposite in polarity. Like the vertical output amplifier, the horizontal output amplifier produces a push-pull output. Remember, push-pull circuits provide greater trace linearity. One of the front panel controls related to this block is the horizontal position control. It moves the trace back and forth and enables the operator to position the display for convenient viewing. With both horizontal and vertical signals applied to the CRT, we see a display that is typical of triggered sweep oscilloscopes. We've taken you on a tour of the basic functional blocks of an oscilloscope. You should have a better understanding of these blocks and their interrelationships to the front panel controls. Whenever you operate an oscilloscope, remember the basic building blocks of the scope, the vertical, horizontal, and trigger sections. That way, you'll be better equipped to match scope setup to your application needs.